I'll be talking about the project I've been working on for the last month, which is the classification of melanoma images through GANs, or Generative Adversarial Networks, VAEs, Virtual Autoencoders, and other ML models. If you don't know what Generative Adversarial Networks are or Virtual Autoencoders are, I definitely suggest that you take an introductory course to it so that you get familiar with this, because this one will basically be going over the implementation of these machine learning models in the project. Just a quick note for the prerequisites. You need to know the basics of PIL, which is basically how to open images, the basics of Matplotlib, intermediate Python, intermediate NumPy, and essentially over here, I used NumPy, sklearn, Matplotlib, TensorFlow, TorchVision, and Torch. I mainly use TensorFlow for most of these things for my semi-supervised image classifier and my supervised image classifier. And I use Matplotlib, sklearn, and NumPy for more data visualization and kind of just manipulating arrays. Over here, you can see that the dataset will be found in melanoma detection.zip. So this is basically what I was training my entire dataset on. Um, Basically, the main premise of this project is to classify images into two separate categories: melanoma or non-melanoma. And the images right now are color 32 by 32 pixel JPG files, where it either ends with asterisk underscore 0 or asterisk underscore 1. And so 0 would be melanoma, and 1 would be 0 will be non-melanoma, and then 1 will be melanoma. Over here you can see that there aren't that many labeled images. There's only 200, and I'll tell you how we actually fix that problem later in the code. We have 600 testing images, and then we have 7,018 unlabeled images. So now let's get to the actual code and inside the project. So since there are only 200 labeled images to work on, like I was talking about before, that's really little to run and actually train an ML model. So I performed some data augmentation on the training images by factoring in their contrast, their brightness, their sharpness, and their color, and sort of just tweaked them around. And this allowed for larger batch sizes and more training images for the model to train on. And additionally, I resized the image to a 100 by 100 image so that the training time of the model is actually reduced. Let's quickly go to my code for these two things. So over here, you can see that I actually defined sharpen, contrast, and color and rotate functions. And then essentially I bounded how much these things can actually contrast, sharpen, or color, depending on how important they were. And then these are basically just my file paths. And over here, I'm essentially actually like augmenting the images. So you can see that I actually have a multiplier of 5, which means that I'm producing 5 images for every one image. So that's how I was able to get, I think it was over 1,200 new images, which is quite a bit. And essentially these images are just tweaks of the original image with the contrast, sharpening, and color actually changed. And I did the same for valid and train. Again, I used a training set of 60% and then a validation set of 40%. But I mainly used the validation for my testing set. And yeah, let me just go to the next part of my code, which is the data resizing. And again, I did the data resizing in order to actually make it easier for the model to train. So over here, I kind of showed an input image over here. This is 200 by 200, but in this case, we only did 100 by 100 because the model can't actually run that fast. And then essentially over here, I just prepared it and saved it into a new directory called train resize from our train process folder. And sorry, this is all the output. And let me just go back. And now let's talk about our 4 separate models. So over here we have a supervised image classifier, which used a TensorFlow backend and achieved an accuracy of 75%. So first we built the training and testing image data generators. We defined the model and then we trained the model, and then we actually ran the model and validated the accuracy. It was pretty boilerplate things. Yeah, using the new augmented and resized images. We used a batch size of 32. We used 10 epochs. And we only used 2 convolution layers and 4 max pooling layers because we didn't want to overcomplicate the model. And let me quickly go to the code right now. So this is the first of 4 ML models that we actually performed. And over here, this is our training and testing image data generators. This is actually our boilerplate code for actually like fixing the layers. This is the summary of our models, and this is how we compiled it. And then over here we actually evaluated it. So over here you can actually see that training the model wasn't too bad. We just used TensorFlow to actually do this. We used an atom optimizer and cross entropy loss. And yeah, so that's how this supervised image classifier works. We got a accuracy of 75%. And the semi-supervised image classifier surprisingly also got an accuracy of 75%. We can kind of just so I can clarify, semi-supervised image classifiers are essentially when you train train on the unlabeled images too by giving them labels, and then you train them to actually get a higher accuracy in the ending. And the main reason that we can attribute this low accuracy is because the images that were actually in this project were not too bright or sharp, so this could actually lead to like a lot of issues in the long run. Like I think let me go back to the data resizing, and I'll show you what I'm talking about. Over here you can see that the image was not that clear, which can cause some issues and errors in actually the classification of the images. So it kind of makes sense that the supervised and semi-supervised image classifier would have the same classification and accuracy. So over here we trained a supervised image classifier with the steps outlined above. We ran predictions using the trained classifier on the unlabeled dataset. We took those labels and provided to the unlabeled dataset and attached it to them, and then we reran the model with the labeled unlabeled data and the label data. So essentially now we're getting more training images to actually test our model. So, and also we need the supervised image classifier to actually run this. So I'll just quickly go here and check our code out. Training a semi-supervised image classifier. So over here, we're essentially just changing the images. Essentially over here we compiled all of our code. So let me just skip this first part. This is all just data augmentation and data resizing. Over here is our main part of the code. So we have the training and testing image data generators. We have our CNN summary, and we saved the model using only 3 epochs this time. We didn't do more because our accuracy was actually already hitting the approaching point over here, and we didn't want to overfit our model. So, and essentially now we just use the same accuracy model again. So this is fairly similar to our supervised thing, except we actually use the supervised image classifier to actually train the semi-supervised image classifier by classifying the unlabeled images and then providing for extra training images. Our next was variational autoencoders. Again, if you don't know what variational autoencoders are, I definitely suggest that you take a course on it. It's part of a larger subset called generative models, which can actually generate images. So over here, we actually trained it on the MNIST dataset. I did not use this for the melanoma images because it would have been too complex, and the variational autoencoder, in my opinion, would not have worked too well. So here are some of the steps we've taken to actually implement the model. Again, I did not use the melanoma dataset, but this is pretty standard, and you can basically tweak this so you can also use it on the melanoma dataset itself. So first, I read in the MNIST dataset. I defined the train and test datasets, and I determined the activation function. I created the encoder using a series of convolutional and dropout layers, and I created the decoder using a series of dense convolutional and dropout layers. And then I compiled the model with an atom optimizer. And I trained the model and evaluated the images made by the encoder, and then I stored it over here. So actually, to quickly go over variational autoencoders, essentially it's encoding the images into an autoencoder. Basically encodes all the images into a smaller dimensionality, and that's the job of the encoder. And the decoder essentially makes that lower dimensionality and actually increases it so that it goes back to the original images. And variational autoencoder essentially tries to mimic the normal distribution function to actually take a subset of this encoded image and produce its own separate images. Again, this is a very high level overview, so I suggest that you take another course if you want to go more into depth about this. And now let's just go to the code to see what we actually did. I chose the no training output because I didn't want to waste too much time. But here is our code. Again, I'll link this at the bottom of the description so you guys can see this in more detail. But right now I'm just giving a brief level overview of it. So here is our definition of the encoder. Here's the definition of the decoder. Again, we're just using convolutional layers and also the dropout layers and dense layers. And over here, I'm essentially just writing the variational autoencoder. This is pretty boilerplate code. It's essentially, honestly, you can just search it up online and you can find this code. There's a lot of good tutorials online actually how to train variational autoencoders in MNIST dataset. I honestly think the hardest part about variational autoencoders is understanding the implementation and why this is actually running. So I suggest that you actually look at a few articles and videos so you can understand this in more detail. And okay, and then our last one was the Semi-Supervised Gan, which achieved an accuracy of 50%, and that may seem less than the supervised and semi-supervised image classifier, but the discriminator network, we at least for me, I think the most probable reason for this was for the low accuracy was the overarching strength of the discriminator compared to the generator. So essentially how generative adversarial networks work is that the discriminator and the generator fight against one another. So the generator tries to produce fake images to show off to the discriminator, and the discriminator tries to figure out which image is real and fake. And essentially it's semi-supervised because it also has a supervised component because it's trying to find out. The discriminator has two jobs: to figure out whether the images are real or fake, and also to figure out whether the images are melanoma and non-melanoma. So again, this is probably the most complex piece of code because we need to train the discriminator to actually train two different sets of things, which can make it a little confusing. So we actually had two separate discriminator models. We had the discriminator supervised, which actually separate between melanoma and melanoma, and with the discriminator unsupervised, which essentially said whether the image was real or fake. And the generator's model is essentially to minimize this classification error produced by the discriminator, while the discriminator's model job is actually distinguish between the real and fake. So they kind of have opposing goals, and this actually helps the model train by itself and produce better images at the ending. So here's our steps for implementing the model. Again, it's very similar. We just train the image and data generators, and this is where it gets a little bit different. We first build the generator network. Use convolutional layers and a hyperbolic tangent activation function. I just use a hyperbolic tangent activation function. That'll be the best and optimal way of running your code. And then you build a discriminator network with 3 convolutional layers and a leaky ReLU and batch normalization. Again, I chose leaky ReLU over ReLU just because I thought it would be safer and more easier so that we won't get those flatline zeros. And then you build the unsupervised and supervised discriminator using a softmax activation layer and a defined predict function respectively. Then lastly, you build a generative adversarial network by combining both the generator and the discriminator network, and you train the model. We use 500 iterations for this example. That may seem like a lot, but it takes a while. Remember that the generator is essentially creating images out of random noise, so it takes a really long time for this generator to actually find out what it's actually supposed to do and actually create those like wonderful images that we want to see. And then lastly, we evaluate the model using the testing set. Again, I couldn't really figure out like what was the actual reason for why the discriminator was failing. But I highly suspect that it was because this discriminator was overarching the generator. So if you go through our code, here we essentially created the testing and training data generators, and essentially this is everything. It's a bit longer than the other one, but it's because there's so much more components to this. We have to account for the validation, the training, and also the unlabeled resize. So that's a lot of components to go through. And for the generator, we have 3 convolutional layers and batch normalization layers. Discriminator, we have 3 convolutional layers again. Over here, supervised, again, we said we're doing the softmax layer, and for unsupervised, we're doing a defined predict function. So this is the predict function that will actually predict whether it's real or fake, and you guys only understand the implementation of this code. I can give you another video if you guys really want to understand it. Next we build a GAN, where we actually add a generator and discriminator, and then we actually train the model now using this. And again, I won't go through the implementation. You guys can see this on my GitHub, but essentially what this is doing is it's first training the supervised using the images and labels, and then it uses it basically uses those predictions to try to predict the supervised loss And again, this is we kind of implemented this code so that we can actually make the discriminator weaker than the generator, but unfortunately that didn't work. So essentially, if this happened, then it would train on the images unlabeled and real, and then it would also change on the generator images, and also it would train on the fake generator images as well. And over here you can see that real is just once, and then fake is just 0. So essentially, real is just 1, and fake is just 0 for all of our labels. So over here we're saying that our generated images are always fake, and our images unlabeled are always true. And yeah, and then we just ran through the iterations, and essentially over here we got an accuracy of 48.75. But again, obviously this can be improved with further testing analysis and actually more implementation of how actually the discriminator is overpowering the generator. So that's the main premise of my project. If you guys have any questions, please put it in the comments below. Yeah, so just to give a really quick overview and recap of what we did a comparison of 4 distinct machine learning models: a supervised image classifier, a semi-supervised image classifier, a semi-supervised generative adversarial network, and a variational autoencoder, and analyzed their effect on the classifying melanoma images. And remember, before we did data augmentation because the testing images, training and testing images were not too good. Yeah. Thank you, and let me know if you guys have any questions in the comments below, and bye.